Today we are going to study about wind energy, chapter 10. Running objective in this chapter: the different design of a wind turbine, the physics of the energy contents of wind, the efficiency of different wind turbine design, and the importance of the tip speed ratio, the geographic distribution of wind energy, the design and wind farms, the utilization of wind energy worldwide, advantages of offshore wind farms. If you click this link, you can about the animation about wind power. It is well made, so before starting this chapter, please watch it. For centuries, wind energy has been used for transportation. This figure shows the one big ship, sailing ship. Wind energy used for grinding grain in the left and pumping water in the right. So this is a traditional four-blade Dutch windmill in Netherlands, and this one is a American multi-blade windmill in Maine state. This figure shows modern wind turbine. The left side one is a horizontal axis turbine, and right one is a vertical axis turbine. So this is a vertical and horizontal. This figure shows two General Electric wind turbine, each rated at 1.6 megawatt. Hub height is 80 meter and rotor diameter is 82.5 meter, so pretty big. And the right one is a Darius rotor in Quebec, so it looks big, but in reality this one is much bigger. This figure shows nacelle of a horizontal axis wind turbine. As you can see here, this one has a horizontal axis, and capacity of this wind turbine is 600 kilowatt. Calculation of wind energy. In order to calculate wind energy, assuming small parcel, cubic parcel of air with dimensions d by d by d, with traveling velocity of v, and this cubic parcel passing through a plane parallel to one of its faces. Then the kinetic energy associated with this mass of air will be like this. This is a velocity of cubic parcel, and this is a mass, and we can calculate the mass of a cubic parcel like this. And this one is density of air. The time required for the parcel of air to pass through the plane is like this: T equal d per v. D is the length of a cubic parcel, v is the velocity of cubic parcel, and the corresponding power is like this. So this is the kinetic energy, and power is energy per time, and we know the time, and we can get this value. Wind power per unit area. The power per unit area is like this, and this is a power, this is unit area, and unit area is this curve, and we can get this equation. If we apply air density 1.204 kilogram per cubic meter, we can get this equation. And if we know the velocity of air, we can get per unit area wind power. The water density is like this, and if we apply this value to here, we can get underwater power per unit area. So we can install turbine underwater, and we can convert to kinetic energy of water into electrical energy. Rotor efficiency. This figure shows wind turbine efficiency as a function of relative air velocity after passing through the wind turbine. So this is rotor efficiency, and this is a relative air velocity. And V is a wind velocity coming to wind turbine. V0 is a wind velocity passing wind turbine. So as you can see here, we can get maximum rotor efficiency at this relative air velocity. It's about 0.24. If relative velocity is higher, that means that the passing wind velocity is close to coming wind velocity, which means that the turbine did not extract as much energy as possible, and if relative velocity is low, it means that it extracts more energy from coming wind. But for some reason, if relative velocity is lower, rotor efficiency decrease. There is some physical meaning, and we can understand it by using mechanical physical calculation. We need a wind turbine that converts as much of kinetic energy as possible into mechanical energy, but there is a theoretical limit. The maximum theoretical efficiency that can be achieved by wind turbine is battery limits, and its limits is 59%. What is battery limit? Battery limit is a theoretical maximum efficiency for a wind turbine. Batts is a scientist concluded that this value is 59.3%, meaning that at most only this amount of kinetic energy from wind can be used to spin the turbine and generate electricity. In reality, common efficiency are in the range of 35 to 45%. Wind turbine works by slowing down passing wind in order to extract energy. If a wind turbine was 100 efficient, then all of the wind would have stopped completely upon contact with the wind turbine, but it's clear that it is not possible. The efficiency of different wind turbine design as a function of tip speed ratio. What is a tip speed ratio? Tip speed ratio is the speed of a fastest moving tip per the actual wind speed. So this figure in x-axis is the tip speed ratio, and y-axis is a power efficiency. Actual wind turbine achieve about 2/3 to 3/4 of theoretical efficiency. Thirty 33 to 37. Tip speed ratio is determined mainly by design of the blade, and this line is a theoretical power coefficient, and this is the ideal batch limit, and this figure shows efficiency as a function of tip speed ratio for different wind turbine design. And this one is most commonly used type of wind turbine design. Cut in and cut out speed. This figure shows power output for a 2 megawatt wind turbine as a function of wind speed. So x-axis is hub height wind speed, and y-axis is power output. So this figure shows power of actual wind turbine from cut-in speed to the rated speed. Power is well described by V cubic. Above the rated speed, there is a risk of damage to the wind turbine due to excess wind power. The speed of the blade is regulated to avoid damage by adjusting the angle of the blade from this wind speed, rated wind speed. Above the cutout speed, the wind turbine is shut down to avoid the damage. This figure shows effect of ground friction and altitude. This figure shows variation in wind speed as a function of altitude for different roughness classes. Circle is roughness class is 0, triangle roughness class 2, square roughness class is 4. So the roughness class is about the surface. So roughness 0 means that it is water. Roughness class 2 typically is filled with some tree. Roughness class 4 typically means that it is the surface is a large city. So as roughness class increase, there is more ground friction. So because scale 1 has a the greatest ground friction, the wind speed is lowest among 3. And but in all cases, if when altitude increase, wind speed is also increase. So as you can see here, the wind speed is greatly affected by ground friction and altitude. Near the coast, wind speed increase offshore, which means that wind blows far from the land, the energy efficiency increases. In this figure, x-axis is distance from shore and y-axis is energy yield. When wind blows far from the land, energy yield increase, and wind from the land is more advantageous than the wind along the shore and wind from the sea for producing electricity from wind turbine. Geographical location. To summarize, wind speed increases substantially by the increasing altitude. Locating the wind turbine at the top of the hill is advantageous. The wind is stronger offshore than on land. Placing wind turbine a few kilometers offshore can provide more energy and also helps to minimize the environmental impact. But we should consider a trade-off between the power output and the cost for construction and serviceability to provide electricity to the human. Wind farms require optimum spacing of wind turbine to maximize power produced per unit area. This figure shows optimum spacing of wind turbine in a wind farm. Distance are shown as a function of a rotor diameter. So in between turbine, there should be they should have a gap from 2 to 4 rotor diameters and 8 to 12 rotor diameter. Multiple turbine can be combined into wind farm. Wind farms require optimum spacing of turbine to maximize power produced per unit range area. If they are too far apart, the wind farm will occupy more range area. If they too close, each turbine will not produce its optimum power. If they occupy more land, it increases construction cost because it occupies a lot of more land and you need more infrastructure. And if you minimize the land area, each turbine will not produce its optimum power because each turbine inhibits power production. Wind power in the United States. This figure shows the average wind speed at a height of 80 meters for onshore and offshore sites in the United States. And as you can see here, this area has abundant source of wind energy. And in the United States, the most viable wind resources are along the Atlantic and Pacific coast and in Great Plains. And this site is a good candidate for wind farms. Examples of wind turbine application on different scale. And this one is a small residential wind turbine. This figure shows medium-size grid-connected wind turbine, and previous one is used for the house, and it does not need to be connected to grid. And this medium size can be connected to the grid, and if it is connected to the grid, it can be used for supplying electricity to public. This figure shows 2.3 megawatt turbine. How height is 980 meter, pretty big, and rotor diameter is 92 meter. Wind farm. So this one shows grid connected wind farm in Amherst, Nova Scotia. The farm consists of 15 wind turbines rated at 2.1 megawatt per each. It's pretty big. This figure shows a schematic of a grid-connected wind turbine system. And for grid connection, you must consider frequency and voltage of your wind turbine to be matched to grid characteristic. This table shows installed wind power as of 2015 for countries with more than 2 gigawatt capacity. China has the best installed capacity, and installed capacity per capita means that the installed capacity per one person in a country, and China has a lot. There are a lot of persons, so in terms of this index, situation is a little bit different, and Germany has the best installed capacity in the world per capita. No, not Germany, Denmark. And Denmark is the best, and Germany is the second best for installed capacity in each country. China is the best, and second best is the United States. Where is Korea? Korea is not so good for wind turbine power generation. I don't know. Recently, Korean government want to make a wind farm, offshore wind farm. How about France? I cannot see France as we like nuclear power. I know that France also like to use electricity from nuclear power. So this figure shows Danish offshore wind farm, and much of Denmark's wind capacity is from offshore wind farm. Environmental consequence of wind power. Wind power has some, although fairly minimal, environmental effects. A description of some of the potential disadvantages of wind power are as follows. First, noise. This is a local concern for residents living within a kilometer or so of the wind turbine. Second is effect on wildlife. For example, risk to birds, bats, etc. Studies have shown that other anthropogenic factors, for example, power lines, vehicle, plate, plate glass window, etc., are of great concerns. And third one is effect on land use. Wind power is more compatible with your land use than any other forms of energy. In many cases, wind power and agriculture or solar energy can utilize common land. The low power density of wind means that substantial land area would be needed to replace current energy sources such as fossil fuel and nuclear. So it is good to apply wind turbine along with other land use to maximize land use efficiency. First one is aesthetics. Is a concern associated with virtually all energy production method. To me, it looks good, but for some people, it may not look good. So it depends on person. I think to me, it looks beautiful. Fifth one is accident. Accident can result from turbine failure. For example, generator fire, tower collapse, or blade breakage, or a combination of these. These are concern for nearby residents and roadways. Summary: the kinetic energy associated with moving air is related to the cube of air cube of its velocity. Wind turbine extract energy from moving air and convert it into electrical energy. Different wind turbine geometries have different efficiency. Available wind turbine depends on location. Generally, available wind turbine energy increases with altitude and distance offshore. Wind farms combine the numerous turbines which can be placed to optimize power production. Development of wind power is being actively pursued by a number of different countries. Okay, so today's lecture is over. Please read the textbook and solve example. One student is telling me that they study example harder for midterm exam and they did not see any from example, but it depends on me. So I expected that you guys study example harder, so I didn't ask about it. But for final exam, you may see them or not. It depends on my decision. So thank you for listening my lecture and have a great day.